Hi everyone. Today we're going to study basic rules for limits involving infinity. The symbol for infinity, positive infinity or negative infinity, does not represent a real number. The symbol is used to describe the behavior of a function when the values are in its domain or range outgrow all finite bounds. For example, the function f of x equals 1 over x is defined for all x not equal to 0. Consider the graph of the function 1 over x. And this is the graph in blue. We can see that when x is positive and becomes increasingly large, the function 1 over x becomes increasingly small and near to the point 0. So we write the limit of the function 1 over x as x approaches positive infinity equals 0. Meanwhile, when x is negative and becomes increasingly large, the function 1 over x becomes increasingly small again and near to the point 0. And we write the limit of the function 1 over x as x approaches negative infinity equals 0. Since the right-hand limit is equal to the left-hand limit, then we write the limit of the function 1 over x as x approaches infinity. This time, this is a two-sided limit, equals 0. Let us see the basic rules for limits involving infinity. For any number k and n, we have number 1, the limit of k as x approaches positive infinity. This is equal to k, that constant function itself. And the limit of k as x approaches negative infinity. This is equal to k. Then we say that the limit of k as x approaches infinity, this is now a two-sided limit, equals k. Number 2, the limit of x as x approaches positive infinity equals positive infinity. And the limit of x as x approaches negative infinity equals negative infinity. Number 3, the limit of the function 1 over x raised to n as x approaches positive infinity. The answer is 0. And the limit of 1 over x raised to n as x approaches negative infinity, the answer is 0. So we say that the limit of 1 over x raised to n as x approaches infinity, this is a two-sided limit now, equals 0. Number 4, the limit of x raised to n as x approaches positive infinity equals positive infinity. And the limit of x raised to n as x approaches negative infinity equals, the answer is positive infinity if n is a positive even integer starting from 2 onwards. Or the answer is negative infinity if n is a positive odd integer starting from 1 onwards. Number 5. The limit of 1 over x raised to n as x approaches 0 from the right. The answer is positive infinity. And the limit of the function 1 over x raised to n as x approaches 0 from the left equals, the answer is positive infinity if n is a positive even integer starting from 2 onwards. Or the answer is negative infinity if n is a positive odd integer starting from 1 onwards. Hi everyone. Today we're going to study evaluate limits involving infinity. This is part 1. Let us see this example 1. Evaluate the limit of the function 1 over x squared as x approaches 0. For our solution, let us remember the rule number 5. It says here, the limit of the function 1 over x raised to n as x approaches 0 from the right equals positive infinity, while the limit of the function 1 over x raised to n as x approaches 0 from the left is equal to positive infinity, provided that n is even and n is greater than or equal to 2. Considering our problem here, we can say that the limit of 1 over x squared as x approaches 0 from the right is equal to the limit of 1 over x squared as x approaches 0 from the left, and this is equal to positive infinity. Since our problem here is a two-sided limit, we can write now the limit of 1 over x squared as x approaches 0 equals positive infinity. Let us note this answer in here. Algebraically, we can observe the graph of this function. You can see here that when x approaches 0 from the right, the graph is going to positive infinity. While coming from the left, the graph is approaching a y value that is positive infinity also. So this is our final answer. Let us see this example 2. Evaluate the limit of the function pi square root of 3 all over x squared as x approaches infinity. For our solution, let us write again our problem, and then let us take note that our numerator here is a constant. By limit law, we can take this constant away while taking the limit of the function 1 over x squared. As you see here, we write pi square root of 3 multiplied by the limit of 1 over x squared as x approaches infinity. We note by rule number 3 that the limit of 1 over x raised to n as x approaches infinity equals 0. It means the limit of 1 over x squared as x approaches infinity equals 0. And we will substitute this value 0 for the limit here. So we have pi square root of 3 times 0. And the final answer is 0. Let us have example 3. Evaluate the limit of the function 2 minus 1 over x as x approaches infinity. We write again our problem here, and by limit law, we can take the limit of each term of the function. So we have the limit of 2 as x approaches infinity minus the limit of 1 over x as x approaches infinity. Take note that the rule number 1 says the limit of the constant k as x approaches infinity equals k. While rule number 3, it says that the limit of 1 over x raised to n as x approaches infinity equals 0. It means to say we can now solve the limit of 2 as x approaches infinity is equal to 2 minus the limit of 1 over x as x approaches infinity is equal to 0, and 2 minus 0 is simply 2. Considering the graph of this function, we can see here that when x approaches positive infinity, the graph is approaching a y value that is 2. While when x is approaching negative infinity, the graph is approaching a y value that is 2. So this is our final answer. Example 4. Evaluate the limit x squared plus 5 as x approaches negative infinity. Let us write again this problem here, and by limit law, we can express this by limit of x squared as x approaches negative infinity plus the limit of 5 as x approaches negative infinity. Let us note that by rule number 4, the limit of x raised to n as x approaches negative infinity equals positive infinity if n is an even number and it is greater or equal to 2, while the answer will be negative infinity if n is an odd number that starts with 1 onwards. And the rule number 1 says the limit of the constant k as x approaches negative infinity equals k. It means to say the limit of x squared as x approaches negative infinity is equal to positive infinity plus the limit of 5 as x approaches negative infinity is equal to 5. So in here, positive infinity plus the constant 5. If we add this, the constant will be consumed by the positive infinity behavior. So the final answer is simply positive infinity. This is our final answer. Hi everyone. Today we're going to study evaluate limits involving infinity, and this is part 2. In this video, we're going to evaluate the limit of a rational function that is of this form. The limit of f of x over g of x as x approaches infinity. The rule is we're going to divide both the numerator and the denominator by the highest power of x in the denominator. Then simplify. Let us see this example 1. Evaluate the limit of 5x squared plus 8x minus 3 over 3x squared plus 2 as x approaches infinity. Let us copy again this problem down here, and as the rule, we're going to divide both the numerator and the denominator by the highest power of x in the denominator. We can see here that the highest power in the denominator is x squared. It means we're going to divide each term of the numerator and the denominator by x squared. So we will have like this. And then let us simplify some of the fractions. We can cancel some terms that we can cancel. And let us write the simplified expression. So the new fraction will be 5 plus 8 over x minus 3 over x squared all over 3 plus 2 over x squared. And from here, we're going to show that we are going to take the limit of each of the terms in the numerator and in the denominator respectively. So it will be like this. Now let us observe that some of the limits have constant in the numerator. We're going to pull out that constant that is to be multiplied by the limit of the respective function. So this will be the next step. Some of the limit here are considered to be approaching 0. Now let us simplify the limits of respective terms. So the limit of 5 as x approaches infinity is simply 5 plus this one here becomes 8 times 0 minus 3 times 0 all over the limit of the constant 3 as x approaches infinity is the constant 3 plus 2 times 0. Simplifying further, this 8 times 0, 3 times 0, and 2 times 0 are all equal to 0. And simplifying now, we have 5 over 3. This is our final answer. Let us see example 2. Evaluate the limit of the function 11x plus 2 over 2x cubed minus 1 as x approaches infinity. Let us rewrite our problem down here. And as the rule says, let us divide both the numerator and the denominator by the highest power of x in the denominator. Let us observe that we have the x cubed as the highest power in the denominator. So we are going to divide each term of the numerator and the denominator by x cubed. So we will have this expression now. And then let us cancel some terms that can be cancelled. And let us rewrite the new expression to be like this. From here, let us show that we are going to take the limit of each of the terms of the numerator and the denominator respectively. So this is how it will look like. Some of the limits have constant in the numerator, so we can pull it out to show that we will multiply that constant after taking the limit of the function respectively. And then we can simplify some limits that will be equal to 0. Now let us evaluate the corresponding limits to be like this. 11 times 0 plus 2 times 0 all over the limit of 2 as x approaches infinity is equal to 2 minus 0. Simplifying further, 11 times 0 plus 2 times 0 will be 0 plus 0 all over the 2 minus 0 is simply 2. And this is equal to 0 over 2, and the quotient is simply 0. This is our final answer. Let us see this example 3. In here, we have problems A and B. The problem A is the limit of the function negative 4x raised to 4 plus 7x all over 2x squared minus 3x minus 10 as x approaches positive infinity. For problem B, it will be the same function, but this one is x approaches negative infinity. Let us begin with problem A. The rule says, let us divide both the numerator and the denominator by the highest power of x in the denominator. So we see here that the highest power is x squared. So we are going to divide each term of the numerator and denominator by x squared. So it will be like this. And then let us cancel some terms that can be cancelled. Let us rewrite the simplified form of the expression. So we have now the limit of negative 4x squared plus 7 over x all over 2 minus 3 over x minus 10 over x squared. And then let us show that we are going to take the limit of each of the terms in the numerator and denominator respectively. So we have now this expression. We can observe also that some limits have constant in the numerator. So we're going to pull out those constants and then multiply by the limit of the function. So it will be like this. For example, this limit of 7 over x, we can write this as 7 times the limit of 1 over x as x approaches positive infinity. So this pattern follows here and also here. And then let us take the respective limits of the expression. And from here, we can see that some limits would be equal to 0. Now, let us take the limits of respective expression. So the limit of negative 4x squared as x approaches positive infinity, we can show that this is negative 4 times positive infinity, and this is squared, plus 7 times 0 all over the limit of a constant 2 as x approaches positive infinity is equal to 2. minus 3 times 0 minus 10 times 0. Let us simplify further. The square of positive infinity will simply positive infinity. 7 times 0 is 0. 3 times 0 is simply 0. And 10 times 0 is 0. Now, this negative 4 multiplied by a positive infinity is negative infinity. All over the denominator is simplified into 2. The negative infinity over positive 2 is simply negative infinity. This is our final answer. Let us copy this answer below problem A. Now let us solve for problem B. We can observe a while ago the functions are similar except that problem B is approaching negative infinity. So we will follow similar pattern of solution. So the first step is to divide each term of the numerator and denominator by the highest power of the denominator. So we have this expression. The next step is to simplify some fractions, and we rewrite the simplified fraction. And from here, we will show the limit of each of the term of the numerator and denominator respectively. The next step is to pull out those constants away from the function, so it will be like this. Next is we can identify those limits that will be equal to 0. Now let us evaluate the corresponding limits. So we have negative 4 times the square of negative infinity plus 7 times 0 all over 2 minus 3 times 0 minus 10 times 0. The square of negative infinity will be positive infinity. And this is multiplied to negative 4 plus the 0 all over 2 minus 0 minus 0. Simplifying further, we have this negative 4 times positive infinity will give us negative infinity over the denominator 2. And the quotient is negative infinity. Let us copy this answer below problem B. So these are the answers for example 3. Hi everyone. Today we're going to study a theorem on limit of rational function as x approaches infinity. If f is a rational function with f of x equals g of x over h of x, the g of x and the h of x are polynomial functions, and they are written in descending form. It starts with the first term a sub m times x raised to m, and the last term is a constant a sub 0. While the h of x has this first term b sub n times x raised to n, and the last term is b sub 0. Where this a sub m and b sub n are not equal to 0. Take note that the a sub m is the coefficient of the first term in the numerator, and the b sub n is the coefficient of the first term of the denominator. Now, the limit of f of x as x approaches positive infinity or negative infinity equals the limit of a sub m times x raised to m all over b sub n times x raised to n as x approaches positive infinity or negative infinity. Take note here, the numerator is the first term here in the function g of x, while the denominator here is the first term of the function h of x. Now, we can simplify further our limit here, and we have three possibilities. This limit is equal to 0 if n is greater than m. Take note that this n is the highest power in the denominator, and this m is the highest power in the numerator. Another possibility is a sub m over b sub n, and this is the answer if n is equal to m. Another possibility is positive infinity or negative infinity. This is the answer if n is less than m. Let us see this example 1. Evaluate the limit of 5x squared plus 8x minus 3 all over 3x squared plus 2 as x approaches infinity. Here, we take note that the highest power of numerator is equal to the highest power of denominator, which is 2. Writing our theorem on this side, we can see that our problem here falls on the second category. The n is equal to m. And this is the answer. It means directly we can write our final answer, and that is the coefficient of the highest power of the numerator over the coefficient of the highest power in the denominator. So we have here 5 over 3. This is our final answer. Let us have example 2. Evaluate the limit of 11x plus 2 all over 2x cubed minus 1 as x approaches infinity. In here, we can see that the highest power of denominator, which is 3, is more than the highest power of numerator, and that is 1. In our theorem, this problem falls on category number 1. So we can write our final answer here directly as 0. This is our final answer. Let's have example 3. Evaluate the limit of negative 4x raised to 4 plus 7x all over 2x squared minus 3x minus 10 as x approaches negative infinity. For our solution, we take note that the highest power in numerator, that is 4, is more than the highest power in the denominator, which is 2. So in the theorem, this falls on category number 3. The n is less than m. And the answer might be positive infinity or negative infinity. And for our solution, let us show first that the limit of the first term in the numerator over the first term of the denominator as x approaches negative infinity. So we have here the limit of negative 4x raised to 4 over 2x squared as x approaches negative infinity. Let us simplify first this expression. We have now this limit of negative 2x squared as x approaches negative infinity. Considering the negative infinity as a common number, we can substitute this negative infinity to the x here. So we have negative 2 times the square of negative infinity. The square of a negative number is positive, and if we multiply a positive number with a negative number, which is negative 2, the answer will be a negative number. So our final answer here is negative infinity. Example 4. Evaluate the limit of the function pi square root of 3 all over x squared as x approaches infinity. In this problem, we take note that the highest power of denominator, which is 2, is more than the highest power of the numerator, which is 0. Take note that our numerator here is a constant, so the power is 0. It means, in the theorem, this problem falls on category number 1. The n is more than m. So the final answer we can write here as 0. Hi everyone. Today we are going to study horizontal and vertical asymptotes. Let us define asymptote. Asymptote is a line that a graph gets closer and closer to, but never touches or crosses it. Here we have a figure, and we have this graph. This red dotted line is what we call the vertical asymptote, while the green dotted line is the horizontal asymptote. For example, we have this function y equals the fraction 1 over x minus 2 plus 4, and this is the graph. Now the vertical asymptote is the equation x equals 2, while the horizontal asymptote is y equals 4. Let us define vertical asymptote. A line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit of f of x as x approaches a from the right is equal to positive infinity or negative infinity, or the limit of f of x as x approaches a from the left equals positive infinity or negative infinity. Now let us define horizontal asymptote. A line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit of f of x as x approaches positive infinity equals b, or the limit of f of x as x approaches negative infinity equals b. Now, given the function y equals f of x, and this f of x is a rational function, and this is equal to g of x over h of x. In this video, we will confine our example for the g of x and h of x are both polynomial functions. Now let us show how to find horizontal asymptote. And our equation is y equals b. For our first step, we will evaluate the limit of the function as x approaches infinity. And this must be equal to a value that is b. And then we're going to write the variable y equals this value b. And this is now the horizontal asymptote. Take note, there is no horizontal asymptote when the degree of numerator is greater than the degree of the denominator. Now let us show how to find vertical asymptote. And the equation is x equals a. First, let us equate h of x equals 0. This h of x is the denominator of the function. And then we will solve for x. The resulting equation for x is the vertical asymptote. Take note, the vertical asymptote occurs when x equals a, produces zeros in the denominator but not in the numerator. When this case occurs, that is y equals 0 over 0 at x equals a, then we say there is no vertical asymptote. Let us see this example. Find the horizontal and vertical asymptotes for the function f of x equals negative 5x squared plus 7x all over 3x squared minus 1. Let us begin finding the horizontal asymptote. The step 1 is we will evaluate the limit of this function as x approaches infinity. We note here that the degree of numerator is equal to the degree of the denominator. So as the theorem says, the answer here is negative 5. That is the coefficient of x squared in the numerator. We write it here over the coefficient of x squared in the denominator. So this is negative 5 over 3. And for step 2, we will write y equals, we will take this value and we put it here. So the horizontal asymptote for this function is y equals negative 5 over 3. Now let us solve for vertical asymptote. Let us equate this h of x, or the denominator, equals 0. So we have 3x squared minus 1 equals 0. And let us solve for x. This negative 1, we're going to transpose to the right, so it becomes positive 1. And let us divide this equation by 3. So we will have now x squared equals 1 over 3. Looking for the x, let us take the square root of both sides. So we have the square root of x squared is equal to plus or minus the square root of 1 over 3. On the left side, we can cancel the radical and the power 2. So we have two values of x here, and when we split it, we will have x equals positive square root of the fraction 1 over 3 and x equals negative square root of the fraction 1 over 3. Take note that the two values of x here, when substituted, do not make the numerator of the function f of x equal to 0. So we have here two vertical asymptotes. So here are the horizontal and vertical asymptotes of the given function. Remember, the horizontal and the vertical asymptotes might happen when the function is rational or quotient, exponential, logarithmic, etc. There are definitely no asymptotes for polynomial functions. I hope you learned something from this video. See you again next time.